Welcome to class number 24. Today let's talk about two topics. We're going to talk about some visibility culling, and then we'll go into something called post effects. First up, visibility culling. Now, visibility culling means to cull out or skip, cut away things that are not visible. So when we're rendering, we render the stuff and it comes out on the camera like so, right? I got my object here, object's on camera. So this is vertices, triangles, and ultimately those are going to be rasterized as pixels, right? And all that gets done by the GPU. Now, what about this object? I just take this object, put it right there, and now it's still here, it's still in the game world, it's right over there, but I know you can't see it. So if I know you can't see it, I can just skip drawing it. I just won't draw it this time. And that will save the GPU having to run all of those vertices through their vertex shaders. It won't have to generate the triangles for them and realize that those triangles are off camera. Once it realizes the triangles are off camera, it won't draw them anyway, but it had to do all the vertices first before it got there. On the other hand, I could have somehow perhaps figured out that the thing was over there and just skipped it altogether. So that's the gist of visibility culling. Is saying if it's not going to be visible, don't draw the thing. So saying that again, we are ultimately going to have a ton of objects. It's like a lot of objects we're going to draw. It can be very expensive. And so if we can quickly and easily chuck out some things that we know we don't need to worry about, we can do this as an optimization. Now, I will say that means we're going to be doing this chucking out. We're sorting the objects of what's visible and not visible on the CPU instead of letting the GPU do all that by itself. So we would do this if we think the GPU is our bottleneck. But if we're solidly convinced that the GPU is doing just fine, but the CPU needs help, then this would be, right, this would be a bad idea. Okay, so pretty much standard practice is to do some visibility culling because we can do it very cheaply on the CPU, or possibly even, if we're clever, make a compute shader to kick that off to the GPU to be done there. So this is, in general, a really good optimization we're going to be seeing in a real game engine. The first and most basic kind of visibility culling is what we call the frustum culling. Now, frustum, that's a $5 word there. That's definitely a vocab word to remember. A frustum is what the camera can see. It looks like this. This is a top-down view maybe of a frustum. The camera's right here. It's looking out this way. And so the right edge of what the camera can see is there. Here's the left edge. And this is the near and the far clipping plane. If we remember those back from our discussion of the camera projection matrix. That's where they are. Now, not shown in this picture is the top and the bottom, but of course we know that those are there. So that's 6 planes, right? That 6 planes makes this sort of chopped off pyramid shape. Like if you look at a dollar bill, flip it over, and you're like, hey, there's a pyramid, only somebody cut off the top and put like a weird eyeball on there, right? Maybe they were rendering engineers and they were trying to draw a frustum. I don't know. So we put the camera there where the eyeball goes, and then we're looking out and we see that pyramid shape. Visualizing that one other way. Here I am, I'm in the middle, I'm the camera, and I'm looking out. And over here I have the right edge of the screen, and over here there's the left edge of the screen, and I got the top edge of the screen and the bottom edge. Now as they come away from my eyes and they head down towards that and then off into infinity, right? That makes that top and bottom plane, left and right plane. And then I have a near plane, and then way out here somewhere I have the far plane. And together those make the frustum. It's called the frustum, and we know that you can only see things that lie inside that pyramid shape. For example, these green objects inside the frustum shape, these are inside. They're completely inside the shape. You can definitely see those two green objects. Now these red objects are absolutely outside the frustum. There's no way you can see those red objects, and so we will cull those. And that then leaves the question of the blue objects. The blue objects are partially inside and partially outside. What are we going to do with them? We will draw them. The simplest answer is, well, just draw them if they're partially inside, and we'll let the GPU clip them off triangle by triangle. So the triangles that stick out onto the screen, the GPU will draw those. The triangles that are over there, the GPU will cut them out. So that's basic frustum culling that works in general for any type of scenario. But sometimes we have more specific scenarios that we can take advantage of to get more efficient culling. For example, let's imagine we're making a game like Crash Bandicoot. If you've never played this before, what it is the players can find along a path that they have to follow, and it's a fairly narrow path, narrow enough that if the camera stays down a prescribed rail down the middle of the path, the player will stay on camera, right? So you can go to the left, you can go to the right a little bit, but the camera is going to go straight down the path as it was designed to be. Knowing this, I know that there's only certain things the camera can ever see. So I could leverage that. And in fact, in that game, they did leverage that. The idea is you might, for example, split the world into sections. I'll take this, I'll call this a section, here's a section, here's a section, right? And I'll say the camera, when it is in this section, it can see that this is what its frustum would look like at that time. And because the camera is fixed, that's all the camera will ever see in that section. So that tells me now that these sections are potentially visible when the camera's in that particular zone, but these cells over here are never visible if the camera is in this zone. So this gives us the opportunity of a very efficient culling algorithm. We can just say, in a tool that runs before the game is even running, we'll do this offline. We'll go and we'll figure out which cells are potentially visible from which other sections, right? And we'll just make a list. We'll just say, we'll just number them. We'll say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And we'll say if you're in, 1, 2, 3, 4, 5. If you're in 5, then you can see 5, 6, 7, 8, 9, 10, and 11. And that's it. And so when it's time to render, we're only going to render those sections, and we're just not even we're not going to do anything at all with those other sections. Okay, so that's a potentially visible set. So here's a slightly more versatile method that works really well for interior games. So your corridor shooter type of game. We'll call this portal occlusion. The idea here is we start with that same frustum that we had from before. So here's a camera, and it's looking out this way. So the frustum for the camera is made by this triangle here. Let's draw this in red. I'll say, okay, the frustum for that camera goes that way and off this way, right? And out here somewhere there's the far plane. All right, so I'll just continue that out. So this is your basic frustum that includes everything. But recognizing that we're in a kind of a claustrophobic interior zone, we can make rooms like room E here. And we'll recognize that room E has this boundary right here, and we're going to clip that frustum against that boundary and just make this skinny little frustum here that we have in that red color. Let me change to green. But maybe there's a doorway, right? There's a doorway here in that wall that we can see through. And so what we'll do is we'll add to our little triangle, we'll add another frustum that looks through that doorway. So it looks through from here and makes another frustum, right? There it is. And we will clip that frustum against these planes, that one, and maybe drop this one on there too. And now we have a new frustum that we will add to the visibility potential set, right? And what about, you know, maybe this back wall here, it has a doorway too. I'll go to like blue. And so we can see through that doorway. So make another frustum. I'm trying to make a frustum right there. It's pretty wiggly, but you get the idea. And I'll clip that one off here too. So now I have, like, I've drawn so far three. I've drawn the blue, the green, and the red frustums, frusta. And what we'll do for our visibility set now is we'll say we can see things only if they're in one of these frustum. So, for example, room G here, room G doesn't land into any of those. And so the entirety of room G can just be cut out. We won't bother drawing that at all. Visibility portals work really well for those claustrophobic interior type of places. But what about the wide open areas of an outdoor type of game? For those, we want to turn it around and do it the other way. We might do, instead of saying there's a window or a door that we might see through that we'll project a portal through, instead we'll say there could be a blocker. Maybe there's a fence or a mountain, or I don't know what it is, a barn that you can't see past. So for those, I'm representing those here as like this occluder and this occluder. So like maybe here's a fence and maybe here's a barn or something, right? We'll say those are objects that you can't see through. So when we make our occluder, when we make our frustum, here's the frustum right here, we will say that there's a frustum made by projecting the camera from the point of the camera out through this object, like so. And here is the near plane of that, and the far plane is, you know, the camera's far plane. So this triangle, it's not a triangle, it's a frustum. This zone here is a frustum, and we know that everything in that frustum is blocked from view. So anything in this region is visible, but anything in this region is not visible. So like these objects will be blocked by this occluder, right? Okay, and the objects over here on the right, these are visible. Now there's a snag with occlusion volumes, and that is illustrated with this diagram here. Let's say the red line is an occluder and the green line is an occluder as well. So we know anything behind this volume, this frustum made by the green near plane, the right edge, the left edge, and out to the far. Anything in this zone is occluded. And that would include the purple triangle. But this green sphere, or green circle, whatever it is, green circle is not completely inside the green frustum. So we will have to draw it. The red occluder blocks the blue rectangle, but it does not completely block the green circle. There's a little bit of the green circle that pokes out. Now we can see that the part of the green circle that pokes out is completely inside the green frustum, and so we should not have to draw the green circle. However, just to try to keep things fast and efficient, the simplest implementation of this occlusion volumes would go ahead and draw that because it is not occluded by any of the individual volumes, and it's actually somewhat difficult to add them together. The last kind of visibility culling I want to talk about is a category called spatial partitioning, where we just take the whole game world and we're going to chop it up in some automated way. And the chopping of the space will allow us to say that certain parts of the space are not visible. Something called a quad tree, where we take the whole game world and we split it up right down the middle into 4 quadrants, thus quad. And then what we do is we subdivide again. The quadrant gets 4 quadrants, and each of those quadrants gets 4 quadrants, and we make a tree. What we'll do then is put each object into the sub-node that it fits into. So like we'll see that this parallelogram, the pink parallelogram, fits into this sub-node, and these 2 triangles can go into these 2 little teeny sub-nodes. How we'll use this for visibility is we'll throw our camera frustum into the scene. Like, let's say the camera is, I don't know, let's say it's right here and it's looking, let's look down. Let's say we're going to look down like so, and there's our view frustum, for example. Now we will take these, switch colors, we'll take each of the nodes in our tree and we'll test them against that frustum, and if there's no overlap, then we don't recurse any deeper down that tree. So for example, this first one, we need to draw that. This bottom one, definitely need to draw that. There's some overlap there. This one, the top right quadrant, is completely occluded. So we will not traverse that one at all. We'll just cut that off. How about this one? The bottom right one, yeah, it does a little bit. So we need to go into the children of that. So I'll change color again. Now we're going to go down a level and we'll test this one, and we can reject that one. Test this one and reject. Test this one and reject. And then we'll test this one, and we will need to draw that one. And so that's how it works. We use the tree-based traversal technique to stop going down as soon as we can. So here I've drawn it more as a traditional tree. And so like, let's imagine we have these nodes in a tree hierarchy. It might look like this. Here's our top node, and there are 4 sub-nodes here. Let's say this one, for example, that's this node here, and there's nothing in it, so it's just null. There is no node there. And then here I have the 2 bottom quadrants. This quadrant must be this one. It's got C and B in it. And this quadrant must be this one. It's got the D, the E, and the F. So here I've got the frustum drawn again, and this time I put it there looking down, and we can see that the A node is not intersecting the frustum, so we just won't go there. This node is this one, that's this one here. It is, so we traverse down to its children and test each of them and find C is visible, yeah, but B is not. So B, we just stop there. And over here we have this one, that's this one, and we don't need to do that one at all. So we'll cut off that entire branch of the tree in one fell swoop. Now, an interesting benefit of this type of spatial partitioning is we can use it for visibility culling, like I just showed here, but we can also use that for collision optimization. Remember I talked about broad phase collision testing by using some kind of spatial partitioning? This is a fantastic option for that same thing, and so you can get sort of a double whammy out of that. Now, the quad tree is a very two-dimensional way of looking at the world and chopping the world up. You're just doing left and right, front and back. But in a full 3D game, you might want to explore an octree, which does this in 3 dimensions. It just, instead of splitting into 4 nodes, we split into 8. So that we have 1, 2, 3, 4, 5, 6, 7, 8. It's the same deal. Now, we don't do this as often because it turns out in video games, even the 3D video games, most of them tend to be rather two-dimensional when looked at from a top-down perspective. You know, even if the players can run around and they can go up and down stairs and stuff, there isn't really that much that we can really leverage as far as occlusion by going up and down. But if you have a game that is very three-dimensional and you know, has multi-tier built into it, then perhaps a full octree is the way to go. So the last spatial partitioning algorithm I want to run past you is a very old one, dates all the way back to the games like Doom, and it's called binary spatial partitioning, or BSP. A BSP tree is a binary tree. Like any binary tree you ever made, you just split things into a left branch and a right branch, just 2 branches of a tree, and then they split and they split and they split as you go down the tree. The way we're going to split a BSP is we're going to make a plane, and it's just an arbitrary plane that will drop in the world somewhere that will conveniently split objects into those that are on the front half of the plane and those are on the back half of the plane. And we'll build this into a tree structure. So for example, here we've got a splitting plane C, and we will split things into everything in front of C is on this side, and everything on the back is on that side. So everything in the back is on that side. And then over here, we're going to see that we split this whole half of the world, right? This whole half of the world over here. We split that again using the A line, the A plane. We'll split that again, and then it has a front and a back. And then maybe inside this, now this is the region that is on the backside of C and on the backside of A. And there we'll split it again with B. So we'll keep splitting and keep splitting along logical boundaries so that we'll try to reject half the world at a time in some kind of meaningful way. So let's say, for example, we have an object. Let's draw a little object. Let's say it's here. Okay, so what are we going to do? We're going to start at the top of the tree, and is this object in front of or behind C? So it is behind C, so that is not there. We're going this way. And then is it in front of or behind B? It is behind B. So we do not go this way, we go this way. And then we say, is it in front of or behind E? It is behind E also, so it's going to go this way down the tree. And so that's how we traverse down the tree to see what is visible and what is not. Now, if at any time our frustum can cut off an entire plane, then we can stop this whole traversal, right? If I look at how a frustum interacts with this, let's make us one. We'll make one. We'll say, I don't know, let's put it right here, looking kind of towards the D, I guess. Let's make a frustum like so. Now, this frustum is completely in front of C. And because of that, like there's the camera looking at that. It's completely in front of C. It's therefore this whole branch of the tree can be rejected instantly. And instead, we will just go down here and start seeing, as we subdivide, are there any like subplanes down in here maybe that we can cut off. Okay, so that is binary spatial partitioning, or BSP.